The farming industry is a vital part of the UK economy and also contributes to our culture and environment. The agricultural sector directly employs about 1.5% of the workforce in the UK, and in 2014 the total income from farming was £5.38 billion, representing around 0.7% of the national economy. Agriculture also uses around 70% of the country's land area, yet the UK produces only 59% of the food it consumes and relies on imports for the rest. The UK population is set to exceed 70 million within the next 2 decades, and with its rapidly growing human population, the pressure on land is increasing. It is becoming ever more important to maximise the use of land, not only for food, but also to support biodiversity and to protect the environment while also providing housing and other uses. There are many ways we could produce food more efficiently in the UK. We have produced a mathematical model to describe how we can find the best conditions to optimise barley yield, by focusing in particular on the optimal time to harvest the crop, ensuring the time available for growing the crop can be used effectively. Our initial assumptions are: weather conditions are constant and have negligible effects on barley yield. The area of the plot in which the crop is growing is constant. Changes in soil have negligible effect on barley yield. Soil contains optimum nutrients and water for barley growth. No competition or interaction between barley plants or between barley plants and pests or weeds. Initially, we expressed yield per plot of barley in terms of weight of each individual plant and the number of plants in the plot. Letting y equal yield, w equal weight, and n equal number of plants, we have y equals wn, where yield and weight are measured in kilograms. We then assume that the rate of growth of an individual barley plant is proportional to the weight of the plant. By differentiating y equals wn and using the chain rule, we can get the following equation. Since y equals wn, we now have a differential equation in terms of the yield. We can solve this equation for y by separating the variables and integrating. This model for yield over time shows that the yield will increase exponentially and without limit, which we know is not valid from looking at previous data for yield and from common knowledge about plant growth. We know a plant must eventually die and therefore cannot continue growing exponentially. We plotted some previous experimental data showing how yield of barley changes over time. This graph shows that the yield does increase almost exponentially initially, but then rate of increase of yield starts to decrease and eventually slows to zero, giving an S-shaped curve. We think the logistic model describes this accurately, as it removes the assumption that plants will not interact with each other, as we know that as plants grow bigger and spread out their roots and leaves, they will compete with other plants around them for many resources, such as nutrients from the soil, water, and light. This will prevent yield from continuing to increase exponentially. To get a model which would give this curve, we went back to the differential equation for yield, 1 over y multiplied by dy by dt equals k, and thought about what would happen if y tends towards the maximum carrying capacity, which we show as capital Y. As y tends towards capital Y, dy by dt, and therefore 1 over y multiplied by dy by dt, will tend towards 0, as dy by dt is the rate of change of yield over time, which, as we stated, will eventually slow to 0. We needed to include another function of y to get a more accurate equation for the later part of the curve. We found this by looking at the already established logistic equation, which models population growth. From this, we deduced that we should let p of t equal y, and that our function of y should be y minus y over y, given the differential equation dy by dt equals ky multiplied by y minus y over y. We solved this equation to get an equation in terms of yield, and then rearranged to find y. We then used the fact that when t equals 0, y equals y0, so y0 equals n multiplied by w0, to find a in terms of initial weight of individual plants and number of plants. As these are both variables we can easily estimate. We got this equation for c, and from this got the following equation for a, which can also be written as this. From this we have the equation we will use for our model. Then we used experimental data to estimate values for average initial weight of individual barley plants and the growth constant k. The value for k depends on many external conditions, and we also found that k changes over time. We also used the data to find an approximate carrying capacity, y, since the yield seemed to tend to a similar value for higher values of n, and the higher values of n are what we are interested in for our model. Using our values for initial weight, k, and carrying capacity, we were able to find an equation for yield in terms of the number of plants in the plot and the amount of time the plants have been growing for in weeks. We were then able to plot a curve from our equation so we could compare it to previous data and validate it. We chose to look at what happens to yield over 10 weeks when between 16 and 64 seeds are planted, as we believe from the past data that planting a number of seeds around this area is likely to give a good yield without being too expensive, as planting more seeds will cost an increased amount of money, and if the yield does not increase a significant amount when more seeds are planted, it will not be worth it and farmers may not get as much profit. We aim to find the best harvest time from this. The graph created from our model seems to show clearly that after about 6 weeks, the rate of increase of yield decreases dramatically and slows to a stop around 8 to 10 weeks after planting. Our model predicts that while all curves reach similar maximum yield, when 32 plants are planted, the yield seems to reach the maximum more quickly. Taking 32 plants as the optimum number to plant in the given area, our model would suggest harvesting at around 6 weeks would be the best time to gain an optimum yield, as after this time the yield does not increase much at all, and the crops will risk being damaged, which may cause yield to decrease again, and may decrease the quality and therefore value of the yield. Harvesting after about 6 weeks may also mean that we can have multiple harvests per season, assuming seeds can be planted again immediately after harvest. This could be a reliable way of increasing yield. Our model has some limitations, as we used experimental data to estimate some values used to create an equation and the graph predicting how yield behaves over time. While we believe our model is valid, as it gives similar results to what we're expecting, it may not be entirely accurate, as it seemed there was no standard error calculated, and so there may not have been repeats in the experiment. We are also not sure what conditions were present in the experiment, whether there was a control or how data was collected. To extend our model further, we could consider exactly how the profit is affected by the yield and the quality of the yield, and get exact values for profit per number of plants to find the number of plants that will give the greatest profit. We could also consider how using fertilizers and pesticides may increase the yield and the quality of the yield, and how quickly the maximum yield is reached under these new conditions. Reducing the plot size while maintaining yield would allow the land to be used for other purposes, including more wild areas to benefit biodiversity or for building to create more housing and services.